Hi everyone, today we are going to study the second order conditions to confirm whether a stationary point is a point of maxima or minima or it is a saddle point. So with this, you will be completing your entire setup of finding maxima or minima of a function of several variables. So let us start today's class. So now let me start with an example. Let us look at this example. Show that 0, 0 is a saddle point of fxy is equal to x square minus y square. So first of all, we must know what is a saddle point. So till now, what we have done? We have done that if a function of two variables fxy is defined on a domain S, okay, then we know that local maxima or local minima, okay, are those points where fxy is respectively maximum or minimum in its neighborhood. Okay, for example, if I say that fxy is maximum at x naught y naught, okay, it means that f of xy will be less than f of x naught y naught, where x comma y belongs to a neighborhood of x naught y naught. So basically, x naught y naught is a point in R2. So how will my neighborhood look like? We have already seen that I have to create an open ball. So open ball means my ball will not be a ball which is including its boundary. So it is going to be a boundaryless ball. Okay, the boundary is not included. So what will be the neighborhood? Neighborhood will be a ball centered at x naught y naught. Okay, and x comma y is a point inside this ball. That is what is meant by neighborhood. So for all x comma y in the neighborhood of x naught y naught, f of xy should be less than f of x naught y naught, and that is what is meant by local maxima of a function at a point. Similarly, if f xy has a local minima at x1 y1, it would mean that f of xy is greater than x1 y1, where x comma y belongs to a neighborhood of x1 y1. And what is the neighborhood of x1 y1? It is a ball with certain radius r centered at x1 y1. So I'll have a ball with x1 y1, and this is the radius r. Okay, and x comma y will be all the points inside this circle. Okay, so these are my x comma y. So that is the definition of local maxima or local minima. We have seen that absolute maxima minima are different than local maxima and minima. Absolute maxima and minima are talked about when the function is defined on a closed and bounded interval, and for such continuous functions we have already done the extreme value theorem in the previous section. Okay, so we know that there is local maxima. When there is local maxima, the definition, the local minima, the definition in terms of neighborhood, and so on. Now it might happen that there is a point which is neither a maxima or a minima. So x2 comma y2 is called a saddle point, okay, if it neither has a maxima nor a minima. Okay, so if it neither is a maxima or a minima, that is, there exists x star y star in the domain of the function such that f of x star y star is greater than f of x2 y2. So obviously x2 y2 cannot be a minima now. Also, there exists x naught y naught in the domain such that f of x naught y naught is less than f of x star f of x2 y2. That means now f of x2 y2 cannot be a point of so x star y, f of x star y star greater than f of x2 y2 means f of x2 y2 cannot be maxima, and f of x naught y naught less than f of x2 y2 means f x2 y2 cannot be a point of minima, because I have a point where the function is taking a much lesser value. So these kind of points are known as saddle points. Okay, now let us see with this example, show that 0, 0 is a saddle point of fxy is equal to x square minus y square. So what is your fxy? X square minus y square. Okay, so I want to show that 0, 0 is a saddle point. So what is f 0, 0? The value of f at 0, 0, that is origin, is 0. Now let us look at the value of f at 1, 0. That is 1 square minus 0 square, that is 1. And let us look at the value at 0, 1. That is going to be 0 square minus 1 square, which is minus 1. So we know that there is a value below 0 and there is a value above 0. So 0 is neither maxima nor minima, and therefore 0, 0 is a saddle point. So what is a saddle point? A saddle point is a point at which a function neither has a local maxima nor have a local minima. Okay, so let us study the second order conditions or second order derivative test for a function of two variables. And this is the test where we are going to consider local maxima minima only. This is not for absolute maximum minima. So what we have to do, first of all, suppose we are dealing with a function of two variables. This is for a function of two variables. Okay. So we already know the first order condition. So what is the necessary condition? That the function has a local maxima or a minima. So the necessary condition for a local maxima minima is that your first order derivative with respect to the first variable should be zero. And the first order derivative with respect to the second variable should also be zero. So here the first variable is x and the second variable is y. Okay. Then what you have to do? Then you have to name such quantities. So a is equal to fxx, that is, del 2f by del x2 or f11 double prime. These are the notations. And then similarly, your b will be equal to f of xy, or that is f of yx also. As per Young's theorem, these two quantities are same if the partial order derivatives are continuous in nature. So we are going to deal with those functions where these two partial derivatives will always be same. Okay. And this is f12 double prime, and c is fyy. Then we calculate a quantity called discriminant, which is AC minus B square. So everything depends on the sign of AC minus B square. So case one, if AC minus B square is positive and A is negative, okay, whatever point we got from the necessary conditions, that is a point of local maxima. Okay. If AC minus B square is positive and A is also positive, we have a condition for local minima. And if AC minus B square is negative, whatever be the sign of your capital A, this is always going to be a saddle point. The only conclusive point is when AC minus B square is equal to zero. So here we can't say anything. So we can have a maxima, we can have a minima, or we can have a saddle point. So let us understand this through an example. Okay. So find the stationary point of fxy, where fxy is minus x cube plus xy plus y square plus x. So what is your fxy? That is minus x cube plus xy plus y square plus x. Okay. So I'll do this step by step. First, you have to calculate the first order partial derivatives, which is minus 3x square plus y plus 1. Okay. And then you have to calculate your first order partial derivative with respect to y, which is x plus 2y. Now the necessary condition says that these two derivatives must be equal to 0. So minus 3x square plus y plus 1 will be equal to 0. And x plus 2y is equal to 0. Now from this, we can get that y is equal to minus x upon 2. Put this over here. So minus 3x square plus minus x upon 2 plus 1 equals to 0. So 6 minus 6x square minus x plus 2 is equal to 0. Okay. So 6x square plus x minus 2 is equal to 0. So let's try to split the middle term. So write x as 4x minus 3x. Okay. Then let's take 2x common from the first two terms and minus 1 common from the last two terms. So this is 2x minus 1, 3x plus 2 equals to 0. And this would imply that 2x minus 1 equals to 0 or 3x plus 2 equals to 0. So the first point is x equals to half. The second point is x is equal to minus 2 by 3. So we know that y is equal to minus x by 2. So this implies that x equals to half, y equals to minus 1 by 4, and x equals to minus 2 by 3, y equals to minus 1 by 3, it is minus x by 2. So 1 by 3. So I have 2 points, two stationary points, half comma minus 4. And another stationary point is q, which is minus 2 by 3, comma 1 by 3. So these are two stationary points that I'm concerned about. Okay. So now I would like to see the second order condition. So I have got perfect candidates, two candidates where I could have a local maxima, local minima, or a saddle point, or none. So let us see what happens. Okay. So now let us try to calculate the second order derivatives. So let's again go to the first order derivative of f with respect to x, which is minus 3x square plus y plus 1. So if I calculate the second order derivative with respect to x, it is going to be minus 6x. And if I calculate the second order derivative with respect to y now, so it should be 1. Okay. So, and then if I calculate fy once more, so fy was x plus 2y. So fyy is 2. Okay. So now let me consider the first point. So the first point is half minus 1 by 4. So what is your a? A is fxx at half minus 1 by 4, which is minus 6 into half, which is minus 3. What is b? B is fxy at half minus 4, and b is 1 only because it is not dependent on any variable now. What is your c? Fyy, which is 2. Okay. So if you look at the discriminant, ac minus b square, so minus 3 into 2, okay, minus 1 square, okay. So this is minus 7. So this is negative. This implies that p half minus 1 by 4 is a saddle point. That means there is neither a maxima nor a minima at this point, and this is confirmed. Now let us go back to our second point. Our second point was minus 2 by 3, comma 1 by 3. So this implies that a fxx at minus 2 by 3, 1 by 3 is minus 6 into minus 2 by 3, which is now going to be 12 by 3, which is 4, that is positive. Now look at b, which is fxy at minus 2 by 3, 1 by 3. This is 1 independent of x and y. See fyy at minus 2 by 3, 1 by 3, which is 2, which is independent of x and y both. Again, so let us calculate d. D is ac minus b square. So d will be equal to 4 into 2 minus 1 square, which is 7, which is positive now. So we have d positive and a positive, and hence we have a local minimum value at this point q minus 2 by 3, 1 by 3. This is how you deal with a function of two variables. Let us do one more. Let us look at this particular example. Classify the stationary points of fxy is equal to x minus 2, ex square minus x, ey minus 2 whole square. So this is our function. So first of all, try to calculate the first order derivative. So let us calculate the derivative with respect to x. Now here y is a constant. So you will be treating e y minus 2 whole square as a constant, and then you will be applying product rule on x minus 2 e raised to the power x square minus x. So x minus 2 का डेरिवेटिव 1 होता है और e की पावर x स्क्वायर माइनस x को ऐसे ही रखेंगे, फिर प्लस x माइनस 2 को ऐसे ही रखेंगे, e की पावर x स्क्वायर माइनस x का डेरिवेटिव होगा e की पावर x स्क्वायर माइनस x ऐसे ही, और चेन रूल से x स्क्वायर माइनस x का डेरिवेटिव होगा 2x minus 1. So if you look at your fx will now be e raised to the power x square minus x कॉमन आ गया, e raised to the power y minus 2 का होल स्क्वायर आ गया, and inside I am having 1 plus x minus 2 into 2x minus 1. So f of x is e की power x square minus x, e की power y minus 2 का whole square. If I solve this, this is 2x square, and then minus x minus 4x, which is minus 5x, plus 2 plus 1, which is 3. Okay. So if I want my fx to be 0, this means that obviously exponential thing can never be 0. Exponentials are always positive. So this means that 2x square minus 5x plus 3 is equal to 0. So 2x square minus 3x minus 2x plus 3 is equal to 0. So x common ले लीजिए, 2x minus 3 minus 1, 2x minus 3 is equal to 0. X minus 1, 2x minus 3 is equal to 0. So x is equal to 1, x is equal to 3 by 2. So I have got two candidates. Okay. Now let's differentiate with respect to y. So fy, now x is supposed to be treated as a constant. So it is x minus 2 e raised to the power x square minus x as it is. And now differentiate e raised to the power y minus 2 whole square. So differentiate it, the derivative of e is e. And now chain rule. So 2y minus 2. Okay. So fy is a 0. Okay. So fy is a 0 if I have, this implies that x is equal to 2 or y is equal to 2. So this is case A and this is case B. Now fx is equal to 0 and fy is equal to 0 simultaneously. We want simultaneously A and B to hold. So they happen simultaneously if x is equal to 1 and y is equal to 2, or x is equal to 3 by 2 and y is equal to 2. So your stationary points now are 1, 2, that is your P and Q, 3 by 2, 2. Understood? So these are your stationary points. And now I will be calculating the second order derivatives, okay, at these points. Let's start. So now let us start with second order derivatives. So uske liye pehle first order derivatives ko dobara likh lete hain. So the first order derivatives were fx was 2x square minus 5x plus 3 e raised to the power x square minus x e raised to the power y minus 2 ka whole square. So now I'm differentiating this with respect to x. So fxx. So again this thing is going to be a constant. So e raised to the power y minus 2 ka whole square. This is a constant. So let us differentiate this. This is 4x minus 5 e raised to the power x square minus x plus 2x square minus 5x plus 3 e raised to the power x square minus x 2x minus 1. थोड़ा सा सिंपल करके लिख लेते हैं. So fxx is, so e raised to the power x square minus x e raised to the power y minus 2 का whole square and bracket में 4x minus 5 plus 2x square minus 5x plus 3 into 2x minus 1. This is your fxx. ठीक है? Okay. So now again we have this fx. Okay. And now let's calculate fxy. So now differentiate with respect to y. That is going to be very easy because ये सब कुछ x में, सिर्फ y वाले को differentiate करेंगे. Okay. That's it. And now we knew that the first order derivative with respect to y was, so it was 2x minus 2, y minus 2, e raised to the power x square minus x, e raised to the power y minus 2 का whole square. So let's calculate fyy. So 2x minus 2, e raised to the power x square minus x को ऐसे ही बाहर रख देते हैं. And अंदर y minus 2 का differentiation 1 होता है. And then y minus 2 को ऐसे ही रखेंगे, e को करेंगे. See, the only thing is that you have to be very patient with differentiation. Otherwise, it's not a very difficult thing. And now let us look at your point P. So point P was 1, 2. So A, which is fxx, at 1 comma 2. So let's put 1 comma 2. So if you look at this expression, so at x equals to 1 and y equals to 2. So this is going to be e raised to the power 0 and e raised to the power 0. And x is 1. So 4 into 1 minus 5, that is minus 1. And the rest of the thing was will be 0, because we know that 2x square minus 5x plus 3 was 0, because I wanted the first order derivative to be 0. And for that, we put this whole thing equal to 0. If you remember, that gave us the values of x. So this whole thing is going to be 0. So my a is coming out to be negative. Okay. And now look at your b. So b at fxx, which is fxy at 1 comma 2. So इसमें तो ये पूरा का पूरा जो चीज है, this will turn out to be 0, because of this expression. That's the beauty of this. And if you look at c, c is fyy. So fyy is, again, we are having at 1 comma 2. So if you're having at 1 comma 2, this x minus 2 is a common factor. So this will become 0. So ये भी 0 हो जाएगा. Okay. So no, but if you look at fxy, okay, I looked at the wrong expression. So this is b is coming out to be uh, x was 1 and fxy, okay, just wait. Fxy should be 0 because it is 1 comma 2. So this is 0. Okay, that is understood. What is fyy? Okay, so in fyy, of course, we don't have x equals to 2. X is equal to 1. So this cannot be 0. So we have to evaluate this. So this is going to be 2. 1 minus 2 is minus 1. Then e power 0. And then we have to multiply this with 1. Then y is 2. So e power 0. And this, since y is 2, this will become 0. Yes. So this is coming out to be minus 2. Yes. So if you look at AC minus b square, if you look at d, so AC was minus 1. So minus 1 into minus 2 minus b square. So this is 2, which is positive. Okay, so A is negative, D is positive, and hence we are going to have a local minima at P. So local minima at P is confirmed. And now let us check the same thing for Q. Just because these expressions are very lengthy, it is very important that we are very careful. So let us do it. Okay. So now my next point is Q, which is 3 by 2 comma 2. Okay, so let us look at A, which is fxx at 3 by 2 comma 2. So again, fxx. So we have to put x equals to 3 by 2 and y equals to 2. Okay. So it is going to be 4 into 3 by 2 minus 5 e raised to the power 3 by 2 whole square minus 3 by 2. And now because x is 3 by 2 is a root of 2x square minus 5x plus 3, this whole quantity will be 0. So let us see what is my a. So my a is 2 times 2. 6 minus 5 is 1. So e raised to the power 9 by 4 minus 3 by 2. This is always a positive quantity. Okay. Now look at your b, fxy. fxy में आपका y equals to 2 आ गया यहाँ पर. So 3 by 2 comma 2, so b will be 0. And let us look at your c. c is fyy at 3 by 2 comma 2. So इसमें आपका ये है 2, 3 by 2 minus 2 and e की पावर एनीथिंग, सो 3 by 2 का होल स्क्वायर minus 3 by 2 ऐसे आएगा. और अंदर क्योंकि ये y equals to 2 है, ये तो 0 हो जाएगा और ये भी 0 हो जाएगा. e पर 0 is 1, so अंदर is 1. So if you see, c is coming out to be, now 3 by 2 minus 2 is negative, so positive, negative, positive. So c is coming out to be negative. So you can see that a is positive, c is negative. So your d is ac minus b square, which is negative because b is 0. A is positive, c is negative, so d is negative. So since your d is coming out to be negative, we have a saddle point at q. So it's not very difficult to decide that whether a point is a local maxima, local minima, or a saddle point for a function of two variables. You just have to follow the steps. Step 1 is that necessary conditions, put the first partial derivatives equal to 0. Find the possible candidates for the stationary points. Then for all those stationary points, you need to calculate A, B, C. And you have to look at the sign of D. If D is positive, we either have a maxima or a minima. If D is negative, we have a saddle point. And if D is equal to 0, the test fails. Then we will have to input the values and apply some logic and decide. Thank you very much.